Hello, welcome back. Today we will be talking about time domain response of second order system. In the previous lecture, we looked at the simpler first order systems and saw how these characteristic exponential convergence to a value show up in all first order systems. Today we will be talking about second order systems. A very characteristic physical system that has second order differential equation is a 1 degree of freedom mechanical system with a mass that, for instance, has a stiffness and damping terms, but in electrical domain and RLC, resistance, capacitor, and inductance, or in other domains, this form also shows up quite frequently. But for now, we'll just look at this mechanical representation of these second order systems. And if we want to start, maybe I can write the equations of motion. We know mass times acceleration, let's call this distance x, equals my force P minus kx minus bx dot. Or I can rearrange things and I'll have mx double dot plus bx dot plus kx equals p. And this is the most general form of a second order differential equation. Maybe you want to divide everything by an m, so the coefficient of x double dot is 1, but this cannot be more general than that. So this is also, again, similar to the first order system. This is simple enough. We can try to solve it analytically using Laplace transform. And here I need two pieces of information. What is the initial conditions? For simplicity, let's give them some name. X at 0, let's call it x naught. And x dot at 0, let's call it v naught. And what we have here is m taking Laplace transform, s squared, x of s, minus s x of 0, x naught, minus this, x dot of 0, v naught. The second one is b times s, x of s, minus s, x naught, plus this one just a constant k times x of s, equals capital P of s, whatever that would be. And give me one more second to group terms together. Factor x of s out. So I have m s squared plus bs plus k over there equals, let's put it this way, I have 1 ms x naught and 1 bs x naught. So what do I have? ms, no, this doesn't have s, that's better. ms minus b times x naught. I have some mv plus mv naught plus p of s. So why did I do this? Because I want to bring this to your attention, that what do these terms mean? So this one will eventually come down and form the denominator of whatever x of s will be. And this is essentially the characteristic polynomial of my system. And this one essentially defines modes of response. These terms contribute to the natural response, and P gives rise to forced response. So already you can see the effect of the parameters of the system that shape the signal, the initial conditions that modulate those shapes and bring out certain values or combinations of those modes, and P of S that can potentially enforce its own roots or poles onto the system and change the behavior however P of S it is. Okay, so this is the basic solution in the Laplace domain. But like before, let's separate these solutions and study them individually. First, let's look at the natural response. Response of this system. So this means that my forcing term P is 0, and I don't worry about this. Only look at the response due to initial conditions. And I'm going to further break this analysis down into multiple cases. So first case 1, we consider the system that has no damping. P is 0, so it's undamped. That's an easier starting point. So if P is 0 and B is 0, my equations simplify quite a bit. So I have x of s. I'm going to rearrange things. This one is 0, that one is 0. I have mx naught s divided by this one, ms squared. B is 0 plus k. Ooh, I have V naught 2. Good to know. Plus m V naught over same thing. M s squared plus k. That's better. So let me factor out one m and cancel it from the top and bottom. So I will have, I take out x naught just to make things look nicer. I have s squared plus k over m plus v naught 1 over s squared plus k over m. And these are the familiar forms of, well, let me make it a little bit more familiar. So for this one to be, I suppose, a cosine, no, sine, I need to have, so this is, if I want to be clear, this will be eventually my omega squared. And for cosine, I need an omega up here too. So that's why I want to multiply it by some square root of k over m and 1 square root of m by k, something like that. Let me just double check I'm doing things right. I am not. Am I? MV. I think think so. Then why did I write it wrong here? No, this is wrong. This is correct, I think. So, I hope it's correct. It is different from my notes, but let's pretend this one looks better than what I have in my note. So right now, this becomes a cosine. This one becomes a sine function. So from here, x of t is going to be x naught cosine of this square root of k over m. And remember that we defined omega n to be a square root of k over m before. So this is cosine of omega n t plus some constant v naught the square root of m over k sine of omega n t. And this looks a little funny, but if you remember from maybe math or maybe even high school math, that cosine of something plus sine of something, it is a little complex added together. You will have some constant sine of same frequency but with some phase. And this constant a depends on these two factors. Phi depends, again, I think it's the tan inverse of this over that, something like that. But it's a sinusoid in the end with a frequency omega n. And if you want to plot this response, x of t, sorry. So it should start from our initial condition of x equals x naught. And it will have the slope that is equal to our v naught. So it is a sinusoid that looks like this. And it has some amplitude that, if I recall correctly, is this squared plus that squared. The whole thing is square root. So long story short, if I have a second order system with some initial condition and no damping and no external input, the response is sinusoidal with the natural frequency of the system k over m, and it oscillates forever. And it is expected because we don't have damping, we would expect an oscillation, and the energy converts from maximum potential energy at these peaks to maximum kinetic energy at these points when we have maximum velocity. And there is no dissipation, so the amplitude of oscillation remains constant forever. So one other thing to maybe consider and think about here, we arrived at a non-damped oscillation. And we should have really expected this, starting from up here, because looking at this characteristic equations, the poles are plus minus square root of k over m j. Both of them are s equal. Both of these are complex conjugate numbers without any real part. And if you remember, from way back that whenever we have these only complex conjugate poles, we have oscillation, undamped oscillation. There is no exponential decay associated with them. So by just looking at this, a seasoned Laplace inverser, a person who is very proficient in that, would immediately tell you, oh, this is a undamped sinusoidal oscillation. All right, so this is case one of undamped natural frequency of a second order system. Let me clean out the board and we continue with case number two, which is natural frequency, but when we have a damping. That would be interesting. So, okay, now let's do another case when we have damping. Again, we are still looking at the natural response, meaning that there is no input, and we have initial condition x0 and v0. And just to remind you, this is the equation for the response x of s. So for now, let's forget about the top part and focus about the poles of the system. So if I want to find the poles, remember that poles, those s's that this denominator is 0, define characteristics of the response. So let's look at the poles. If I want to solve this, s becomes minus b plus minus the square root of b squared minus, wait a minute, 4mk, where do I have 4? Oh, 4, yes, 4mk divided by 2m. So those are the poles of this response. And this square root is very important, very interesting. So let's look at this. Let's consider two conditions. If B2 is less than 4mk, yeah, let's do that. If B2 is less than 4mk, this one becomes smaller than that. So the whole square root becomes the square root of a negative number. And then we have some complex number. So in this case, I'll have complex conjugate poles with some real part to it. And the real part is negative, assuming that all these m and b are positive. I'll have a complex conjugate pole, a pair of complex conjugate poles with negative real parts. And this means my response will look like something. Eventually I'll have some terms, some constant terms, e to the minus something, t sine of something t. The response will be a damped oscillation that eventually reaches 0, settles down to 0. Conversely, if b is bigger, b squared is bigger than 4mk, so this becomes a real value, and both of my poles will be real. And because now I'm subtracting something from b squared, this square root will be smaller than b, and adding something to this minus b, which is smaller, both of the poles will be negative, which means I'll have, let me write it down, real poles, and assuming that B and M are all the parameters are positive, those will be have with negative real part, or two negative. Let me do this. Do it this way. Poles that are negative. And if I have two poles, these will be my modes of response that will be of the type e to the minus something t. And this is just an exponential decay. So my response will not have any oscillation like the top case. So you see something interesting happens here. Depending on the relative values of B, M, and K, kind of there is a switch between modes of response. And that switch happens at the value where B squared is 4mk, or when B is 2 square root of mk. This is a critical point that separates the two modes of response of the same system. And very aptly, this is called critical damping, usually shown with B sub c. B sub c is 2 square root of km. This is critical damping. Depending on what mass and stiffness you have, there is one value of B that can decide whether your system will have oscillation or will have a pure exponential decay. Now this B can give us, well, let me put it this way, that depending on value of K and M, every system might have a different critical damping. It is similar to the condition that we worked with in first order system, that we had only one term, tau, that we could use all across systems, and it defined the characteristics of the response. We kind of like to do the same thing here. So let me define a variable called z. This is the Greek letter z. Very similar to zeta, but I think zeta doesn't have two thingies, only one. This is zeta. Anyways, I could be wrong, I don't know. But anyways, I call this z, and this is a dimensionless variable, and that is the ratio of my actual damping divided by the critical damping value. And this one is called damping ratio. Damping ratio. Similar to tau, this one can be used to define a family of responses that are shared across all systems. As long as they have the same zeta, or no, z, they will have similar behavior. So going back to here, if I want to summarize it, if this z is, if I want to put it here like that one, if z is less than 1, so b is less than b critical, or b squared is less than 4mk, I'll have damped oscillations. If z is bigger than 1, I'll have exponential decay, So this is some kind of e to the minus something t sine of something t. And this one will be a combination of a couple of e to the minus something t's. And if I have z equals 1, so if z equals 1, meaning that b equals b critical, meaning that b squared equals 4km, meaning that this is 0, and I will have two poles, both of them at minus b over 2m, so I'll have repeated poles. And if you remember, repeated poles means that I have one term that looks like this, and another one that looks like t multiplied by that. So I'll have two terms, one e to the minus something t, and e to the minus something t. It is still an exponential decay that doesn't show any oscillation. So these are the kind of descriptive behavior of the system. And if I want to also plot to give you a little bit of visual. Oh, I have good colors. Good. So let's start from this one. I should have written it up there. So if z is bigger than 1, I'll have some kind of exponential decay like that. This is z bigger than 1. If I keep increasing z, let me still write it with this green color, I'll have faster and faster exponentials. So for instance, this is z equals 2, this is z equals 1, and until some point that this becomes as fast as possible, reaches 0, arrives at 0, and it stays at 0 forever after. This is z equals 1. So the system behaves, it has the fastest decay without showing any oscillations. And maybe if I try one last color, if z is less than 1, I'll have, well, this doesn't look very nice. I will have an oscillation. Sorry, I couldn't plot it better. Well, maybe I could. Let me do this. Pretend I didn't draw this. And this is z less than 1. I'll have some oscillation that eventually damps out and settles at 0. So these are the general shapes. I'll have better animation later when I show you actual equations of the responses. But this is what we should expect from just by looking and thinking about the responses. So think about this for a second until I clean the board. I come back with more math. All right. So maybe one other thing I should have written before erasing the board is, so I have defined these terms: critical damping, damping ratio, and before we had natural frequency of the system defined as k over m. This was the frequency of the oscillation when we had 0 damping. It is important to remember this is for an undamped oscillation system. Now, let me rewrite this denominator. I'm going to divide everything by an m. So the coefficient of s squared is 0. I'm just looking at the denominator. So I have s squared plus b over m s plus k over m. That's the denominator. And I'm going to rewrite this in terms of these values. So B over M is B is zeta times or Z times BC. Z BC over M, and BC is 2k 2 square root of km, 2 square root of km times what did I do? Times Z divided by M, and I can cancel out 1 square root of M from top and bottom. This becomes 2 square root of K over M Z, or 2Z omega N. And this term K over M, obviously we had it before, is omega N squared. So if I use these to rewrite my denominator, my denominator will look like this: S squared plus 2Z omega N S plus omega N squared, maybe equal to 0, but this is the denominator of my system that defines the characteristics. And as you can see, I need two variables, or two parameters, I should say, to define how the system behaves. One is omega n, and the other one is zeta. And the combination of these two, depending on whether the system is overdamped, underdamped. Did I define these? I don't think I did. I don't remember. Let's do it now. So maybe I did. I don't remember. So these omega n and z define the shape of the response of the system. And if z is bigger than 1, we call it overdamped. Overdamped, since the system is overdamped. If z equals 1, it is critically damped, and if z is less than 1, it's underdamped. So it would be nice if I had defined these terms before, but sorry about that. So overdamped means the system has so much damping in it that it is not allowed to oscillate. Conversely, underdamped, the system is kind of relaxed and loose, so it can afford to oscillate. There is not enough damping or resistance force that prevents it from oscillating. And at critical damping is the intersection of the two, that is the system just is about to show oscillation, but it doesn't. That is, the system is at critical damping. Okay, I should have done this earlier, but that's fine. Now you know. And going back up here, if I know the frequency, the natural frequency of the system, and the damping ratio, I can fully know how the system behaves. Well, given that I know the initial conditions. All right. So I'm just going to write down the equations for any of these. Feel free to skip ahead. It doesn't matter if you see the derivation. The derivation is relatively straightforward but cumbersome, that you have to separate these terms into forms that you're familiar with. You have entries in the table, Laplace table. But if you do that, all of the above, you will arrive at equations for this system. So let's start with underdamped. So in this case, I will have two complex conjugate poles with negative real parts, and it is expected that in the end my response is going to look like an exponentially decayed oscillation. So x of t is going to be e to the minus z omega n. Before I write, no, do I do that? Omega, no, I don't do that. Omega n t, this is my exponential decay term that must be multiplied by an oscillating function. So this system, it's an exponential decay multiplied again by a summation of something sine of something t plus another thing cosine of same thing t. And this is a sine of omega t shifted with some phase. So everything, all of this is going to be some constant a e to the minus omega z omega n t, some sine of omega dt plus some phi. And here omega d is what is called the damped frequency. Omega n is undamped or natural frequency for the undamped system. Omega d, the oscillations will be different if we have damping, and that is omega n 1 minus z squared. So remember this, that as we have damping, we will start to have slightly slower and slower oscillations. So my frequency will be scaled by a number less than 1, which makes sense. If you add resistance to the system, it does not like to go as fast or oscillate as fast. So this is, let me draw a box around this one as well. This is the undamped, underdamped oscillation. Another case that I can write the equations is overdamped. And again, feel free to skip the video until we arrive at the actual equation. So, well, actually, you don't. Maybe you don't need to. Maybe you do. I don't know. X of t is going to be a very large coefficient that I'm not even bothering to write down. E to the minus z omega n plus omega n square root of z squared minus 1 over t plus another coefficient e to the minus all the same thing, z omega n now minus omega n square root z squared minus 1 t. So this a and b are constants that depend on x0 and v0, similar to here, but they are bigger in terms of shape. The function is not as simple as that, a little bigger. And we have two exponential decaying functions with some rate. And the combination of two exponentials is still an exponential decay with possibly a slightly kink, either going up and coming down or completely coming down. Depends on the values of a and b, which in turn are dependent on the initial conditions. That's overdamped. And the last one, critically damped. Critically damped is the simplest of all. X of t will be x naught e to the minus omega n t plus omega n x naught v naught t e to the minus omega n t. All right, and this is critically damped. That is a combination of an exponential decay and a timed exponential decay. Also, this one eventually comes to zero, exponential reaches zero, but it has the characteristics of slightly shifting the signal. Yes, that is what it is. So let me give you a little bit of visual how these functions look like. Okay, this is good. So we are talking about the natural response of the system. And here I have set my omega n to be equal to, that is constant. What I'm going to change is this parameter z, my damping ratio. Let's start with z equals 0. This is the condition that I have zero damping. So b equals 0, and it is the case that we had before. So my response is a sustained oscillation that never dies out over time. As I increase the damping ratio, now you see I have an oscillation that starts from some initial condition, x equals 1, and comes down and eventually settles out at 0. If I keep increasing my damping ratio, the strengths of oscillations become smaller compared to the strengths of the damping. So damping is restricting more and more of the motion, and we see less and less damping. Keep going on. Dampings above 0.8 or 9 don't show a lot of oscillation, but still it exists. So if I can zoom in, you should still be able to see some oscillation, that it comes down, goes up, but it is almost non-oscillatory until we reach the value of 1. Z equals 1. This is the critically damped system. And you will see as I increase Z, this is the fastest decay to 0 without showing oscillation. And if I keep increasing, the system becomes just slower and slower, but maintains its non-oscillatory decay towards 0. So these are the responses of the natural response of a second order system, varying by parameter z. If you change omega, it's going to remain more or less the same, except that you will have faster oscillations, but it doesn't change the characteristics of when the system has oscillation in case of underdamped, and when it doesn't show oscillation when it's overdamped. All right, so that is that. I only have a little bit left that we can talk about. Let's talk about the forced response, specifically a step response, and we can wrap this up. All right, so now let's look at, we already covered a few cases for the natural response of the system. Well, we covered everything, I think. Now let's take a look at the forced response of the system. And remember, forced response is the one where the initial conditions are 0, but we have a non-zero input. So the entire response of the system is due to the forcing term. So if you recall, the differential equation taken into Laplace domain is going to be x of s, and there is no other terms that have, here I would have these initial condition terms, but they are 0 plus x of s times b plus x of s sb times k equals this p of s. And if I want to rewrite this, x of s is going to be sum 1 over m. Let me write it this way, u of s, not u, p of s over s squared plus b over m s plus k over m. And if you remember, we just rewrote this in terms of z and omega n, so it's 1 over m p of s over s squared plus 2z omega n s plus omega n squared. So depending on what function this p of s is, it can modify the shape of the response. For instance, it can add its own roots to the denominator or poles to the system and change the modes of behavior. So the response will depend obviously on what input p we have. Like before, the useful one that we heavily rely on is the step response. Where p of t, the input as a function of time, is some value a u of t, where u is the step. So if I want to draw it again, this is p of t, this is t. I'll have this kind of input coming at a. So in this case, if I write this p of s, taking Laplace of that is going to be a over s, and substituting that up to here, my x of s is going to be 1 over ms, well, a over ms, same thing as I had before, s squared plus 2z omega n s plus omega n squared. So all we need to do is to take inverse Laplace of this, which is doable, fairly easy, but needs a little bit of tedious manipulations. I'm going to skip all the steps. In the end, I arrive at a over m omega n squared 1 over s minus z omega n over s plus z omega n squared plus omega n squared. And the last term is s plus z omega n divided by same thing, s plus z omega n squared plus omega n squared. So it's the same expression written and separated into terms, such that now we know what Laplace inverse of any of these are. Um, this one is an exponential. Well, which one? Yeah, both of them. What? Yes, this one, both of them are exponentially decaying oscillations with the rate of decay being this sigma omega n. This one is a sine, that one is a cosine. And that one is just a constant step value. So if I take the inverse Laplace, it's going to be, let me have my notes, a over m omega n, what do I have squared? So this is 1 minus e to the minus z omega nt. First one is sine of omega n, omega oh, this is not omega n, this is omega d. Remember, omega d was omega n times the square root of 1 minus z squared. So that's better, omega d t, and minus e to the minus z omega n t cosine of omega d t. Do I have it right? I think so. I hope so. No, I don't. No. I'm missing a term. I'm missing a term here. Let me make it a little, make it a bit do this. This is going to be z. Minus there, a over omega n. Okay, that's it. That's x of t. So again, this one is a constant. One is good. We are happy with it. I have some. If I factor this exponential decay, I have some a times sine of something plus b sine of same cosine of same thing. So that combination is just a sine of omega dt with a phase shift. So it's all going to be a over m omega n square 1 minus some a e to the minus z omega n t sine of omega d t plus phi. And this is the step response of an, maybe I should have emphasized this here, that we are assuming an underdamped system. It didn't matter here. Did it matter? Yes, it mattered here. Here we assume z is less than 1 for this to work. But you could also do the same calculation when we had overdamped system. So now let's look at this. That I have a function, this one. This is essentially an exponential that oscillates and comes to 0. And if I have 1 minus that, means I have some function that reaches, oscillates, and eventually settles at 1 with some scaling factor. So if I want to show it how it looks like, this one. So that's the natural response. We already covered this. And this is the step response. Again, you can solve it based on different values of z. When we have z equals 0 and we apply a step force to our system starts to oscillate back and forth. It comes to some reference value 1, which is supposed to, but because it has inertia, it overshoots, it continues with its velocity until it reaches some maximum and coming down. Now if I increase z, now my system again starts, comes here, overshoots, but eventually comes back down and settles at 0. And increasing the damping ratio, it starts to eat into the oscillations and shrink the oscillatory behavior of the response. And the overshoot becomes smaller, so the system is more slowly reaches and it doesn't have as much inertia to overshoot until the critical damping that it shows no oscillation, and after that it just an exponential increase, exponential asymptotic increase until it reaches the set point. So this, let me go back and maybe 0.4, 0.3. So this oscillation, this overshoot, an oscillation is something we didn't have in first order systems. This is fundamentally something that systems of second and higher order can exhibit. And you can somehow think of it as the presence of an inertia within the system that allows this overshoot. If you didn't have that inertia, there wasn't any essentially, well, inertia in the system, and it would follow more submissively to the input. It didn't show any resistance to wanting to keep its current state. All right, that is all we have for the second order systems. We can further continue and analyze the response of the system to ramp and other inputs, but I think that is good enough for now. That gives us some intuition about how the response of a second order system, both a natural response and a step response, look like, and how we can characterize those responses using the damping ratio and natural frequency of the system. Okay, the only thing I have left is stepping up from second order system. Maybe I can write it with this color, that we don't fully analyze all higher order system, but step response of higher order systems. So let's quickly go over that too. When we have a higher order system, doesn't matter what system looks like, as long as it's a linear time invariant system, the response will eventually, in the Laplace domain, look like something like this. So I'll have some B naught S to the power M plus all other derivatives to B M minus 1S plus BM divided by a similar polynomial but order n, and we usually have it with coefficient 1 plus a n minus 1s plus a n, and it will have some forcing, and the response will also depend on the forcing term p. But in the case of a step response, this one is 1 over s. And so I have a signal that is characterized by this Laplace form. So if you remember, anything that looks like this, we can start to divide it into partial fractions, with the denominators being s minus the poles of the system. It will look something like this: a over s, some constant, maybe let's call it a naught, or no, I don't know, it doesn't matter, some ai s minus pi. These are the real poles, and if we have complex conjugate poles, remember we didn't like to break them apart because it was easier to work with the complex conjugate forms to give us those sine and cosine functions. And we can write bk, this is a very general form, s plus, well, no, not b, this is big B, capital B, some bk, this is summation over a, this is summation over k, bks plus zk omega k plus some ck omega k 1 minus ck squared. My marker is dying. It's the end of the day. Divided by s squared plus 2zk omega k s plus omega k squared. So these are just terms. This is essentially some b s plus some c, but written using this combination of parameters. So we can always do this and convert it to that form. And what you can see, it is essentially a combination of some first order response and some second order response. So any higher order system will fundamentally have only these kind of characteristics, with maybe one exception that, well, no, even then it is considered here when we have repeated poles. Some of these need to be s minus pi to the power, I don't know, n, the order of that pole. But nonetheless, the response will be something of this form, that is a combination of first order and second order responses. So always we will have these exponential terms and exponential oscillatory terms. And yeah, that is a very maybe interesting property of linear systems, that you can always combine simpler order responses to create higher order responses. So I showed you everything. That's all I have for now. So let me, for a few minutes, recap what we have done so far. I stand here. We started by first developing mathematical models for our mechanical systems. And with these two lectures, we started looking and analyzing in detail how the time behavior of those systems depend on the parameters and how they look like. And this concludes the first section or first chapter of the course. In the upcoming chapter, there are two other major sections in the course. We will use these techniques that we have learned and try to analyze more complex systems using two sets of new tools that we will learn. One is the idea of transfer functions, and the other one, the idea of state space representations. So with that, I leave you with these notes and see you next time.